Hi class, this is number 8. Again, this is one I made notes on, but I've seen so many people have questions about that I decided to go ahead and make a video about it too. So this is number 8 on 6.2. A study was conducted on students from a particular high school over the last 8 years. The following information was found regarding standardized tests used for college admittance. Scores on this SAT test are normally distributed with a mean of 1,039 and a standard deviation of 203. Scores on the ACT are normally distributed with a mean of 22.4 and a standard deviation of 4.8. It is assumed that the two tests measure the same aptitude, but use different scales. If a student gets a SAT score that is the 25th percentile, find the actual SAT score. So this problem is kind of opposite, and let me just show you kind of what's going on. A typical problem asks you to find the probability that a particular student would have, a score of 101 or higher, or 1100 or higher. That's a typical question that you would expect on a problem like this. What's the probability that a particular student has a score of 1100 or higher? And what you would do in that problem is you would find 1100, you would shade the curve that of everything. If you're looking for higher than 100, what's probably a bit higher than 100, everything to the right where the higher numbers of 1,100 all are located. And then we would use the normal CDF function and input, the lower bound here. We would make the interval. The interval starts at 1100 and ends at positive infinity. Like I said, with the TI-84 calculator, you'd use positive 1 E is 99. It's not the letter E I'm using, it's the EE, which means E for exponent. Well, that's what I'm gonna say. That's how I'm gonna remember it, to help me remember. Okay. That's positive 1, just to re-emphasize, it's positive infinity, it's positive 1, E99 if you were, okay, so that's your lower bound and your upper bound. So you go 1100, 1 E is 99, and you put your standard deviation 1139, and you put your mean. These are the SAT scores, so make sure to look at the mean of the SATs. And then standard deviation of 203. You put that in, and then you get this area, which would equal this area would equal the probability the random student would have a score of 1100 or higher, but it also would tell you the percentage of students that have a value, a score of 1100 or higher, or what we call the relative frequency of the students, or the percentage of students with that quality. Okay, so that's what the normal CDF function does. With this problem, it's doing the opposite, right? It's telling you the area under the curve, hey, the 25th percentile. So the 25th percentile means that 25% of the data is below this value. So they're saying there's an unknown value on the x-axis, and 25% of the data, I'm going to try to make it 25%, is to the, they said, when they say 25th percentile means that this score, that the student, the 25% of the population scored this score or lower. So the percent of the population who scored this score or lower is 25. which would mean the area under the curve to the left of that value is 0.25. So they're giving us, we input into the function normal CDF of some unknown value of negative infinity, which would we say negative not 1 to the E9. They put to this unknown value X, and they put the mean and standard deviation, and they got an answer of 0.25. They're giving us the answer they got after they put in the calculator normal CDF, right? They're giving us the answer they got was 0.25. So this problem is, I call it an inverse norm problem, because we need to use the inverse, it's the opposite of what the normal function does. The normal function, you put the X value in and the mean standard deviation, and then you get the area and the curve. This function, you give it the area under the curve, and it'll spit out the X value along the horizontal axis, such that that amount of the data is underneath that X value. Okay, so let's see how we would do that. Let's on a TI-84 calculator, you can go to second vars and do distributions, choose distributions, and then you can choose inverse norm. It's like INVENORM or something like that. You just put in the only thing you have to always, whether you're using a class calculator, whether you're using a class calculator or TI-84 calculator, the area that goes in always has to be the area that is to the left. Okay, so this would be 0.5, because there are situations where maybe in a problem they would give you all the area to the right of a certain, or maybe just particular, for whatever reason, the area to the right. So then you could do 1 minus that to find the area under the curve to the left, right? Because there's a complement. This black area and that white area under the curve, they have to add to 1 whole. Okay, so that could happen too. So that's not the situation this time, but that can happen. But let's see how we would do this on a TI-85 calculator. Inverse norm, put the area to the left, then put your mean and standard deviation. And was 203, and then there you go. Then you would get your answer. It would give you the SAT score that you're looking for. Okay, let's see how we do this calculation on your class calculator. It's really easy. I love this class calculator. You click on stats. By the way, if you don't know how to, what I found out is you can click on, the plus sign to add another, just add another tab, in your internet browser window. And then you can just type in classcalc.com/graphing-calculator, and then this will pull up for you. So it's pretty nice and easy formula. Anyway, so we go to stats. Then I go to distant plots. I go to, first I do like I'm doing the normal distribution, and then I put the 10.39 they said was the mean of the SATs. And then it said they also wanted that it was 203 was the standard deviation, I believe. Okay, then you close off the parentheses, so shift 0 and to close off that parentheses. Next, we go to stat distance next, and then over here it says inverse CDF. Now it's waiting for you to input the area to the left. So we put the 0.25. And this down here is exactly the answer we want. It's 902. So it's telling us if you have a score of 902, that means that 25% of the students had this score or smaller. Yeah, okay, so let's just double check it. There it is, 902. All right, let's move on to the second part. It says, what would be the equivalent ACT score for this student? So we use Z-scores to compare, we call apples to oranges. So numbers, systems that the numbers don't clearly, like the numbers don't really relate, but they're measuring the same thing, but we can kind of still compare the numbers by using Z-scores. So what would be the equivalent ACT score for this student? Well, what we have to do is calculate the number of standard deviations that this number is, which is the Z-score of this number. So how far is this number away from the mean? The 139. That's basically what we want. And literally, we're gonna take and we're gonna find that distance, and we're gonna measure how many standard deviations is that distance away from the mean. And of course, the larger number, the more we're getting into these tails, the more that's a very rare and different results from all the rest of the students. So let's go ahead and use use this Z-score. So how do we calculate a Z-score? You take your data value or X value, you subtract the mean, and then you divide by the standard deviation. This is going to tell us kind of the location of this data value, like how odd is this data value in respect to all the other data values that are there. So I plug in 902 is the data value that I'm trying to like translate and be like, what is this of the ACT score? So this 902 minus the mean, which is 1039, divided by the standard deviation, which is 203. And so let's just do that calculation quickly. (902) minus 1039 divided by 203. Okay, so it's giving me a negative 0.6748. We want to be kind of accurate here. We keep a lot more decimal places than we typically would because this is affecting our next answer. Negative 0.674876. Okay, that's good enough. Usually you want to keep as twice as many decimals as they're asking for accuracy in your final answers here. So you would want to keep at least 2 decimal places, but I'm doing extra duty. I'm just gonna do 4. I'll do 4, not 6, is ridiculous. Especially when they only want 1 decimal place of accuracy. Not sure why. Okay, I guess the computer is like, you will keep all 4, all 6. Okay. All right. Now, so this is telling me that this is it's not quite 1 standard deviation, or it's like right 0.6, it's close to 0.5, right? So it's like a half a standard deviation below the mean. So it's somewhere, it's the standard deviation happens right at the inflection point, like where it's halfway down the hill. So it's telling me it's right in between here and here. So it's the graph is really high right here. So it's a pretty common result. And so if we want to find out what ACT score is similar to that, we can calculate what ACT score also has the same Z-score. So you can use a formula and just make, this is the number of standard deviations away from the mean, right? That away from the mean. So it may make sense to you that when you do this calculation, you're going to, and to get the value you want, you're going to take the Z-score times by the standard deviation, because that's the number of standard deviations. So if we multiply that standard deviation, then I'm just going to get back a regular distance now. So now I get back to the regular distance away from the mean it is. If I add back the mean, because when I originally did the calculation, I did the data value minus the mean, so I'm adding back the mean, right? Then it's going to get me back to an actual value of test score value along the x-axis, and not like a z-score that's just kind of telling me where it is within the data. So I plug this, but the difference is I'm going to use this. The difference is now I'm going to use the mean and standard deviation of the ACT scores. And when I do that, it's going to give me the ACT score that had that Z value. So I plug in the Z score that I got times by the standard deviation of now we're talking we're in the land of ACT scores now. So the standard deviation of the ACT scores is 4.8. See, if you were that far, if you're 0.67 standard deviations away in ACT, in ACT talk, that's 4.8 of those, away. And then it would be the mean of the ACT scores is 22.4. So let's calculate this. Okay, so I multiplied the 4.8 times the negative 0.6748, and then I'm going to add the 22.4. And I get this 19.1 value. 19.16, which would probably be rounded to 19.2. I think they want one decimal place. Okay, so and I mean, to me, it's pretty straightforward, because that's literally the definition of a z-score, the number of standard deviations away from the mean. So if I want to know the actual data value, and I have a z-score, then I just take the z-score times by the standard deviation, add the mean. So this 19.2, and let's just double check our answers here. Yep, 19.2 exactly. All right, let's look at this last problem. It says, wait, I have it over here already. If a student gets an SAT score of 1506, find the equivalent ACT score. So for this one, you just take this number and do exactly what we did, but now we're going from SAT to ACT again. So this basically, literally, we're going to do the same thing again. So we're going to start by finding the z-score of this number. We're going to use the same formula there, the data value, which is actually, or X value. We usually just put an X here. Minus the mean. Remember this first part, we are using the mean and standard deviation from the when we're calculating the z-score, we use, this mean and standard deviation of whatever the original number was. So the data value is 1506. And this makes sense. I want to know how far away is this number of question. I'm trying to figure out how odd it is. So I want, first thing is how far away from the normal number is it? The typical number, the mean. Okay, and the standard deviation is 203. So let's calculate what that is. $15.06. Tons. Let's clear this all out. 1506 minus 1039 divided by 203, and I get 2.3. Because it's positive, we already knew this, but this number is above the mean. This is an above average student, right? So it makes sense that our z-score is positive. Sometimes people are shocked that the z-score is negative. Well, it just means that that's a below average person, right? Just means it's below the mean. Oh, I was supposed to get more decimal places, otherwise we're going to get it wrong. Hold on. 1506 minus 1039 divided by 203. Oh, it's really, basically, I put 004. I wonder why I didn't really put more down. All right, and you guys know the next step is, now that I turned it into a z-score, now this is the number of standard deviations it is above the mean. So it makes sense. If I want to know what value has the same z-score as this one, but is an ACT score, now I'm going to use the mean of the ACT scores and then the standard deviation of the ACT scores. And I say, hey, how far is this away from the mean? So you start at the mean. You could do it this way, all right? And then you say it's this many standard deviations away from the mean. So it's 2.3004. Oh, I was trying to write the formula down. The mean plus the z-score times the standard deviation, which is the same, but I just switched the addition there. Sorry about that, but this is not, so this is your data value, or X value along the x-axis that is going to pop out for us, our ACT score. The standard deviation of ACT scores, let's look at that again, was 4.8. And the mean, I feel like this second problem here is like redundant. Like, why did we just got done with that? Thank you very much. Like, why? I guess they want me to give you extra practice here. Just look at the x value. Okay, so now be careful the way we're doing our math, that we're following order of operations. We have addition and multiplication going on here. So we must do the multiplication here first, and then we add that answer to the 22.4, okay? So if we do anything differently, otherwise, we're not gonna get it right. So I get 33.44. So rounded to one decimal place, 33.4. So let's look at it. And there we go. So that means that if a person got a score of 1506, when they took their SATs, and another person, they were sick and just whatever, they didn't take their SATs, but they could take their ACT, and they got a score of 33.4. The second, I guess, none of them could boast to each other, I did better than you, because actually these scores are the same, are saying the same score. If you look at it in a way of like compared to how much better than everybody else they did, they both did equally better than everybody else, right? Because they both have a z-score of 2.3 above the mean. So, all right. Not that we should be comparing ourselves to anybody else, because all of us are talented and all of us are smart and intelligent just in our own ways, really. So, yeah. So anyways, have a nice night, and you take care, okay? Bye. Please make sure to message me if you have any questions. Bye.